So this is a summer 22 P42, and it's a capacitor discharge question. But first, we're going to try to answer the easy part, which is to define the capacitance of a parallel plate called capacitor. So this C is Q over V. Okay, so we can call this the ratio, basically the charge stored, 2 marks, or so I should be more specific, charge stored on a single plate of the capacitor, that will be Q over V. So per unit potential difference across the plates. So to make sure you don't lose marks due to technicality, the first thing is if you mention this is charge per unit potential difference, this is already M1. But because this definition is worth 2 marks, so you need to think about, okay, this charge is where on a single plate, okay? And the potential difference is where? Across the plates. So these two would be your A. Okay? Of course, if you don't get your M1, you won't get your A1, because your A1 won't make sense without your M1. All right. So part B, you have 2 capacitors connected in parallel to a power supply, E. And you're asked to show that the combined capacitance is the sum of the 2 capacitors individually. Explain your reasoning. You may draw on the diagram if you wish. So I look at this is 3 marks, I guess. The first thing I want to think about is they are parallel. So obviously the potential difference here is the same as the potential difference here. So potential difference across C1 will be the same as the potential difference across C2. Would I feel safer if I write it down in the sentence? Yeah. Okay. And they're also parallel to the battery. So I'm going to just equate these two. Write it down in the sentence now. So potential difference across both C1 and C2 is equal to the e.m.f of the battery. So then V1 equal V2 equal E. Teacher, I don't write sentence, I write equation, can? Can, but it's clearer if you write a sentence. Okay? You're only going to write it once anyway, because it's only going to sit for exam once, right lah? Right, next part. Let's think about the charges, okay? We know that current, which is sort of like related to charge flow, the current was split into 2. So let's say this is I2, this is IT, total current. This is I1, the current through capacitor 1. And this is I2, the current through capacitor 2. But instead of current, the one we are concerned about in capacitor is charge. So I'm going to draw the flow of the negative charge because the electron is the one that is moving, right? So your negative charge electrons, they have to travel like this. So this is QT, the total charge. Okay, and then when they reach this junction, some of it, Q1, will begin to populate C1. Some of it will continue, Q2, which will then begin to populate C2. So this part here is Q2. So just by looking at this diagram, I can see that the total charge entering the junction is the same as the charge going out of the junction into C1, and also directly straight from the junction into C2. Kind of like Kirchhoff's law. It is actually Kirchhoff's law. Right, so I'm going to write that down now. Second thing to know is that the total charge will be equal to the charge stored in Q, capacitor 1, and the charge stored in capacitor 2. Okay, then the second thing is to use is that since Q is equal to CV, so this will be the total capacitance, the potential difference across the total capacitance, which is actually E. But I'll write everything first, C1 V1 plus C2 V2. So VT is equal to E, and furthermore, V1 equal V2 equal to E. So I guess I'm going to write this one as E. And since all of this is the same, I can cancel them out. Same. CT is equal to C1 plus C2. Proven. So the key places to show working, number one, is the potential difference. Make sure you show that. Number two is the charge. The total charge is a charge stored in individual capacitor. And finally, you substitute Q is CV, and then you simplify in a way that people can accept. This is another mark, 1 mark. So derivation is pretty straightforward. It's always doing 3 steps. Number one, write the relationship of the potential difference and the power supply. Are they equal or are they the sum? Number two, write the relationship of the charge flow. So the charge stored in the capacitor and also the supply. And number three, use the equation Q is equal to CV. You may need to rearrange if needed. Substitute. So you need to manipulate or adjust a bit, but we substitute back into whatever equation you have written here or here. Very standard one. Okay, because these are kind of obvious. So then you don't really need to memorize it. You can sort of follow. I know the relationship between potential difference depending on the arrangement. I know the relationship between charge, and I can use Q equal to CV to substitute and simplify. All right, moving on to the meat of the question, part C. So part C here, we sort of have a pretty interesting circuit because we have a 12-volt power supply, but we also have a 2.7 mega ohm resistor. And I have a switch here that I can flip between X and Y. I can adjust that, right? So if I connect the switch S to X, what I'm doing is I'm connecting the capacitor to the power supply and I'm charging the capacitor. Okay, so I'll write down here for people. Sx is when the capacitors are charging. What about Sy? If we connect to Sy, we connect through the resistor. Okay, so resistor will use up your energy. Capacitors discharging, loses energy. Kind of makes sense, right? Battery will give you energy, resistor will take away energy and become hot. All right, so right now you are asked to show the combined capacitance. Well, these two are series arrangement. So 1 over total capacitance is 1 over 22 micro plus 1 over 47 microfarad. If I press my calculator, it is 15 microfarad. Nice and easy, 1 mark. Don't have to spend too much time. This line of working is what we're looking for. All right. The next part, it says here that the two-way switch is initially positioned at X so that the capacitors are fully charged. Okay. Use the information in C1 to calculate the total energy stored in the two capacitors. So you've got 2 capacitors, and I want to find the total energy. So let's think about what are the equations that we have. Energy stored in the capacitor. Energy stored. Did I give you the equation? I also don't know. Let me see. Equations given. Energy of the capacitor is not given to you. Unfortunately. So you can use half QV, half CV square, or half Q square over C. All right, they're actually the same equation. We just keep substituting Q equal to CV to simplify. But in this case, I want to find the total energy. So I think about what I know. I know the total capacitance, that is 15 microfarad. I also know the total potential difference across both capacitors. Let me show you in the circuit. Look at this circuit. Because it's connected to the battery, here all the way to here must be 12. So the total potential difference is 12. So I'm going to use the equation with C and V. E is equal to half CV squared. Because why? I lazy to find Q. I don't need to find the charge stored in the capacitor. Didn't give also. Didn't give what I want to find. I don't do work for free. No marks, don't want to find. Okay, so 15 microfarad, and then the potential difference is 12 square. All right, let me press my calculator. This one I cannot use my brain. Right. So we have half 15 micro times 144 or 12 square. So this will be 1.08 times 10 to the power -3. You can leave your answer as 2SF. So that's what I will do. Teacher, why you leave 2SF? Because all the values given is 2SF lor. Look here. 12, 12.7, 22, 47. All of these are two significant figures. I just follow the question. Okay? Get used to following the question. Don't feel bad that you round a significant figure. It's fine. All right, part 3. The two-way switch is now moved to position Y. So we are ready to discharge, and the capacitor is connected to the resistor. Determine the time taken for the potential difference across the 22 microfarad capacitor to become 6 volt. Okay, let me draw that in a circuit for you first. Okay, so for ease of reference, I have the circuit here, and it says that I want to find the time taken for the 22 microfarad capacitor, which is this one, to be 6 volt. So V equal to 6 volt. But what is V naught? Because your equation was V is equal to V naught E negative T over RC. Okay, so I think let's list down what we have. We want V is equal to 6 volt. Okay, and looking for T. Do we know what V naught is? If you're thinking V naught is 12, then I will unfortunately say it's not 12. 12 is everybody, whole thing. V naught is less than 12. Okay, because they are in series. Whatever it is not 12. Not 12. Okay, so we're only looking across the 22 microfarad capacitor. Okay, what about R? I guess R is pretty straightforward. 2.7 mega ohm. But what about C? Oh, this one. Should we use 22 microfarad? 47 plus 22 microfarad? Okay, so there are actually a few things we need to find. We need to find out what is V naught. We need to figure out which capacitance to use. Then only we can find T. So many hidden steps. Yeah, lor. Okay, sure, never mind. We'll do it step by step. So I guess part 1, I want to find V naught first. That seems like the easier one to do. So I can say that the potential difference V across the 22 microfarad capacitor plus the potential difference across the 47 microfarad capacitor is equal to 12 volt. Okay, so this 22 microfarad capacitor is what I want to find, but I guess you're kind of like, I need to write down the relationship first and see how I can move things accordingly. Okay, what else do I know? I know that the charge stored is the same. So I guess for ease of reference, maybe I'll call this capacitor 1 and I'll call this capacitor 2. Okay, I'm finding the initial PD. Okay, so I know that the sum of PD must be 12 volt, but also at the same time, I know the charge stored in capacitor 1 will be the same as the charge stored in capacitor 2, which also will be the same as the total charge. Alright, so these are things that we know. So capacitor in series, they share potential difference, and then the charge is the same. But also, I think about it, right? Since Q is equal to CV, okay, they have the same charge, so C is actually inversely proportional to V because Q is constant. Now, if you are like long-time fan of the channel, you will remember me saying ratio is your best friend. Can you simultaneous equation based on the first two equation I've written? Sure, but where got time? This thing is only 3 marks. So what is actually expected of you is for this state to be able to directly think of what kind of ratio you can use. Not solely solve simultaneous equation already, but if you have to, don't let it stop you from completing the question lah, okay? Examination is a race for time, but life is not. Okay, so understand exam is not your value, but for this question, yeah, we kind of have to use ratio because that's a little bit faster. You can look at some other recordings where I actually solve the simultaneous equation, but today I'm going to use ratio. Okay, so I'm going to just say C1 over C2 is equal to V2 over V1. And what are we looking for? We are looking for V1. So V naught is V1. Here to here is V2. Okay, so I'm going to write a ratio first. C1 over C2 would be 22 microfarad over 47 microfarad. And V2 over V1, I don't know. But I do know that V2 plus V1 is 12. So since I'm looking for V1, can I substitute V2? V2 will be 12 minus V1, right? Okay. So they are sharing lah. The whole point here is they're sharing the potential difference. Anyway, I will move this over. 12 minus V1 over V1. Okay, probably need a bit more space. Excuse me. So I'll cross multiply. 22 V1 is equal to, need the calculator, 47 times 12. I cross multiply 564 minus 47 V1. Okay, I just cross multiply. V1 go up here, 47 with 12 gets 564, and 47 V1. So if I take 47, add that to 22. Oh, this will give me 69. Someone is laughing now. So my V1 is 564 divided by 69, which would be 8.17. I guess you can write 8.2 lah. Okay, so what we're looking for is just V1. It is not 12, all right? So there are many ways to do this, but the whole point here is you want to find the potential difference because they are sharing the potential difference. Okay, they're sharing. V1 plus V2 is 12. This is the first identity that we need to think about. Okay, and the second one would be because Q is equal to CV. So then we can say that C is inversely proportional to V and write out this equation. Okay, if you are good at doing ratio, you don't need to substitute directly. You can just tell that because they are inversely proportional, you can use the ratio relationship directly, but this is also okay. All right, so once you found V1, what to do? We have this one already. So now we need to think about which capacitance do we need to use. Are we going to use 22 because the question is asking about 22, or are we going to use 15? Okay, so to answer this question, I'm going to zoom into the circuit a bit and explain a bit about what is going on during the discharging process. Okay, when your switch is connected to this point here, I'm going to delete this one. Your charges here and your charges here, they will begin to backflow. Okay, so a charge will flow through here, Q2, and charge will also flow here, Q1. And because they are done by induction, all this negative charge will reach this positive plate and neutralize it. And then the other negative charge will go through one round, through this, and come here to neutralize this orange color positive plate. Okay, so I repeat. When we close the switch, the electrons here on the second capacitor and neutralize the positive plate of the first capacitor. And the electrons on the first capacitor will zoom and neutralize the positive plate of the second capacitor. So in this discharging process, whatever happens to capacitor 1 happens to capacitor 2. They're in this together. Charges that is induced in capacitor 1 is also in capacitor 2. Because if you remember, the charging process is done by induction. Then I become more negative, so my neighbor have to be positive. Okay, that's the idea of induction. So because of this, the discharging process involves both capacitors. I need to be able to use both C1 and C2. So in this case, the answer to which C to use would be this one. And then let me write it down for you. Because discharging involves charge, induction, and flow across both capacitors in series. That's why. So we're going to use 50. Okay, we can now substitute. We are ready. V is equal to V naught E negative T over RC. The final voltage is 6 volt. The initial voltage was 8.17. I'm going to put 8.2. So 6.0, 8.2. Okay. V naught is 8.2 volt. And I'll have e to the power of negative t over r is 2.7 times 10 to the power of 6, and c is 15 times 10 to the power of negative 6. Okay, mega, micro, thank goodness they cancel. 10 to the power of 6 and 10 to the power of negative 6 will go away. Alright, so I'm going to rearrange the equation a bit. This will be 6.0 over 8.2, and this is e to the power of negative t over 2.7 times 15. Okay, so how many steps you do from this point on depends on your ability to familiarize with the exponent equation. If you are not familiar with this, take your time. If you are, you can skip a few steps. You see this exponent here, I'm going to bring it over, becomes ln. Okay, then this will be 6.0 over 8.2. Because the exponent is brought over, then the power remains t over 2.7 times 15. Then I can press my calculator, which I will do so now. So ln 6 over 8.2 times 2.7 times 8, the negative is 8. Lost the negative for a bit. So remember there's a negative here. So negative 12.7. Which is 12.7 or 13 seconds. Okay. So this question is quite a sneaky one. Because a lot of times students may actually forget that the 12 volt is across both capacitor, but then they only ask for one capacitor. So there's this extra step you need to do to find what is the initial voltage of this one. This one, 8.17. Okay. So this extra step actually takes time. And normally this calculation is worth 2 marks, but right now because I guess they expect this to be easy, so this will be C1, just 1 mark, if you manage to find V1. Okay. And then if you use the right equation, like this, you substitute the right time constants, which is 2.7 mega ohm and 15 microfarad. This will be another C1. And then everything else, other substitution, leading to the final answer is A1. Okay, dash E. So some of you may be thinking, and by the way, the question is solved, but I'm going to talk a little bit about options. Some of you may be thinking, teacher, I can find the initial capacitor across C1, like what you did. But why can I also do it by looking for the whole thing? So like in this question, I focus my entire effort on the 22 microfarad because it's required by the question. But if you want to, you can consider both as well. Okay, so this section, I'm going to talk about what that looks like. Feel free to, if you're watching the recording, feel free to, if you understand, maybe it's okay to move on. But let's say, for example, you want to look for an alternative, okay? And the alternative will look something like this. It is not less step, it's just, in my brain, it's the same thing, but instead of looking at one, I look at both. So the initial state is at 12 volt, and this is V naught. Okay, and now, if this is 6.0 volt, I sort of like, I'm going to change color. If this is 6.0 volt, it's what the question is telling us. I want to know what is the entire potential difference here, V. And then I substitute into the equation and find. So the final potential difference across both capacitors. Also can. Okay, so you can find this and use the equation V is V naught E negative T over RC. Okay, so again, the method to find the total V is by ratio, so you will also go through the same process. Both are fine because they are in series. So whatever happens to one capacitor, so happens to the other one as well in terms of charges, right? But I think this is where I'll stop the discussion for this question. It's a lot of work for 3 marks, and I think this is one of those questions where they get to choose the candidate that actually is really prepared for exam versus those who are yet familiar with the equation and also the procedures, right? But don't worry, things get a little bit easier in winter 20.